All right, let's take a look at the LC circuit. So I have one loop here connected with this switch. That switch is open. And I'm going to close this switch, which is going to instantly charge up the capacitor. Alright, so once that's charged, there is the potential across it, and we're going to measure that with the voltmeter. It's going to be whatever the battery was, which should be 9 volts. Here I also have a current meter, so once we close this switch, the attraction of these particles, so basically this negative wants to be attached to these positives, so they're going to move through the circuit. Alright, so when the negatives are here, they move until they attach all the positives, and it becomes negative, and they just keep oscillating back and forth. If we look at the current, you can see that the current is oscillating back and forth. When the current stops, it's whenever the capacitor is fully charged. When we have the maximum current, you can see it's when the capacitor is completely discharged. By moving these leads back and forth, you can see that the voltage across both elements is always the same. And if you didn't see that, we can rewind the video here. Right, so from measuring across the capacitor, if we move it up there, so it's not making a reading, so it jumps. But you can see that the curve on the voltage graph never changes. And because there's no resistor in there, it's like a frictionless situation, so it'll just oscillate back and forth forever. So here is a look at what's happening with the energies. So this is the starting point when the capacitor is fully charged. Think of this as a spring block system. This would be whenever we pull the block that's on the spring to its maximum amplitude, and then we let it go. Right? So as this capacitor discharges, of course the current increases. Whenever the capacitor is fully uncharged, that's when we have the maximum current, maximum magnetic field, and its charge starts to build up. And this is halfway through. All right, so we don't make an entire cycle for an entire period of oscillation until the capacitor is charged with the positive plate on top. So we can see from here to here that that top plate is negative. So that's just half of the curve. It has to come all the way back up to get back to its maximum. And the total energy always remains the same, since there's no resistor taking the energy out in the form of heat. And because it's analogous to a block spring, the equations will also match up here. Over here are the equations that we had for oscillations. This term right here stands for the maximum speed throughout its oscillation, and that would be when there's no stretch. To relate these two, the charge is analogous to the spring stretch, and the current analogous to the velocity. So we just change the equation by putting q's where the x's are, and putting I's where the V's are. All right, and if this is the maximum speed, this is the maximum current. All right, continuing to look at this, we have the block on the spring. The force that's causing that block to accelerate is the spring force. Spring force is negative kx. The differential for acceleration is dv dt. And solving or writing that differential equation in terms of 0 gives us this. Now, we did this before to figure out the period of oscillations. So for this situation, we would write this differential in terms of the x position. So the derivative of velocity, which is acceleration, is the double integral of position with respect to time. Dividing every term by m moves it underneath that k. And then from this equation, we found that this term is what ends up in our period equation. So that period is equal to 2 pi times the square root of whatever ends up here, k over m. If we do the same thing for the LC circuits, where k is related to 1 over c, right? So remember that x was related to the charge on the capacitor, so k is going to be the 1 over c. Now the mass is going to be analogous to the L. So substituting in these values into this equation, we get that form. If we write that in terms of the second order derivative of the total charge, like we did over here for position, the di dt will be the second order derivative of the charge with respect to time. I forgot my squared over here. And that's going to be plus 1 over c times the charge, and that's going to equal 0. But there was this L right here. So we're going to divide everything by L, which puts that L down here. So same thing, this term is going to be what ends up underneath the square root sign for the oscillator. And the last things are the energies. All right, so the energy for a capacitor is 1/2 1 over c times q squared, q squared. And the energy for an inductor is 1/2 L I squared. Remember that this is like a spring, so the spring was 1/2 k x squared, where we already established that k is 1 over c, x is q, and this acts like a kinetic energy equation where L was mass and current was velocity. From the image of the cycles of the oscillation, and it had the energy bar graphs there, you can see that total energy never changed. However, the initial energy would have been whatever was stored on the capacitor. And then, so that would be the total. and then the energy at any other point in time, we'll even say that's initial, would be the addition of really the potential plus the analogous kinetic, because it's still a potential. And if we're going from max to min for the maximum current, there would be no charge on the capacitor at all, so this would end up going away, so that the total before would have to equal the total once the switch is closed. And that's all you have to understand for LC circuits. So if you understand the mechanical oscillations, just know what is analogous to what, and you can just substitute them into those equations, and you'll be fine.